into MPS, so that then other people who actually use MPS in real life will show them their exciting projects and how they use MPS on that. Okay, so before I start explaining what is MPS, I need to make sure there's someone actually interested. So how many of you know already what MPS is? All right, so not all people. Good, and some of you are not, so you probably know just a little bit here and there. I also met a few people in the corridor. They told me they've seen MPS like 6 years ago. So that information that they probably learned 6 years ago is now obsolete. MPS has evolved pretty rapidly, so it's a different tool than it used to be before. In brief, MPS is a language workbench for domain-specific languages. Now, you came to the JetBrains office, so you probably have some connection with JetBrains. So how many of you use any of the JetBrains tools? Great. Well, I never got that response at conferences, so it's like 100% of people here. Is there anybody from JetBrains itself? Just to just to filter out the people who actually use it. All right, good. So, well, if you know any of the tools, which are they actually? IntelliJ IDEA, anyone? Yeah. Sea Lion, PyCharm, PHP Storm or WebStorm, RubyMine. All right. Well, thank you. Well, all of them are represented. So language workbenches are very similar. Actually, when you see MPS on my computer, you'll realize, well, it's very similar to the IDEs you know. Because part of what workbenches do, they allow you to write code with assistance, just like all the other IDEs. But on top of that, they allow you to play with the languages, to define them or tune them and change them. And that's what I want to highlight here and show it here. Now, this tool is no longer an experimental project, but it's a project that is a real tool that people are using. And some of the customers will show how just after my talk. I should mention that MPS is an open source tool, so you can get it for free and play with it. You can get sources from GitHub and look how that's all implemented. Well, to best illustrate what MPS can do, I'll show you an example, but not a real-life example, but a simplified one, so that you all can relate to it and you all can sort of understand the principles. So I picked a domain that is well-known, voice menu systems. Systems where you call in a bank, right, and you've got a menu, press 1 for invoices, press 2 for live operator, and so on. Now, when you have a system like this, when you want to set up such a system in your office, you have to use, well, technically, well, there are several providers. One of them is called Asterisk. That's the one we use at JetBrains. And in order to configure it, you have to upload audio files plus configuration files to the server. And the server will then interpret that code and somehow respond to incoming calls. Now, obviously, the best qualified people in company that should define voice menus are people from the customer relationship departments or marketing departments. They know what campaigns you're running, what you want to highlight. They've got studies on what the structure of a good menu should actually be. But if you give them this, I mean, you can imagine the result, right? So typically you need an IT person that understands this cryptic syntax to work in cooperation with a marketing person to build a menu system. And once they finish it, and then you come with a new requirement, please change that to something else, you again need the technical guy to change things. And if you have a new person coming for the marketing into the marketing department, and you tell her, here is the definition of our voice menu, get familiar with it and make changes to it. Again, the information about the structure of the voice menu is lost. I mean, it is there, but it's difficult to get it out. So that's a typical problem domain that MPS can help solve. So we built an IDE for defining voice menus. And it looks like IntelliJ IDEA, right? Oops. So you've got all these panels on the side. You've got a very similar structure of the menu. If you click on a thing, you've got an editor opened with your code. Well, and here you've got a language that is used to represent voice menu. So you can define menus and submenus, assign numbers and some titles, and you can write text that should be set to the person that calls. And when you start editing, you get a very similar set of assistants, like the options that you can choose. You can get intentions. You can get code completion, navigation. All these things that you know from other IDEs. So you can search for usages and do all that. And in addition to that, you've got an extra panel of the available actions on the right side of the screen. So an IDE that you can really play with a language that is dedicated to the task at hand. And if you make a mistake, like you type the same button, use the same button twice, it will give you an error message. So static code analysis in play, telling you, hey, you've got this number twice in the menu. Probably you should reconsider. Similarly, if you use a symbol that is not on the phone keyboard, again, you get a message. And the message is domain specific, right? It's not possible null pointer exception or array out of bounds. It's really like telling you, hey, this doesn't exist on a phone keyboard. So even the error messages are customized to the domain. And when you're done defining the menu, then you just run a code generator that will generate the cryptic format that you need to deploy to the server. It will also generate the audio files that need to be uploaded, and all that can be then uploaded to the server. Or you can have it run on the continuous integration server. So this can be done overnight, and in the morning you've got a new version of voice menu applied to the server. So just like the same process that we know from developing other kinds of applications, now applied to developing voice menu systems. You can save this store this in Git. You can have versions and branches of voice menu definitions if you wish to. Okay, so what we got was a domain-specific language, a language specific to this one particular domain that raises the level of abstraction to a level where marketing people can actually operate this tool and this language. And in addition to that, you've got tooling, the tooling that we know from IDEs. And then there is a generator that generates the cryptic syntax. It separates nicely two areas, the problem domain, how to define a voice menu that's efficient and it meets our needs, from the implementation domain, how to actually do it in that cryptic syntax, how to implement a good voice menu definition. So schematically, we've got a language definition in which programmers, or well, people who understand the domain, create their models. There's an analogy to, you can have a Java as a language and you create programs. You have voice menu language, you create voice menu definitions. And then there's a generator associated with that language that takes your model and creates the code that needs to be uploaded to the server, generated code, which relies on some libraries that are necessary to actually function properly. Now, you're not limited to one generator, though. Instead of generating the asterisk format, you can generate XML. So now this is the same thing, but generated as XML document. So that could be appropriate for another tool, another voice menu system, or for some analysis tool that can tell you whether the structure of the voice menu is, correct. Maybe there are some unreachable things. Maybe you have duplicate entries. You could have a tool that can find that as long as you provide it with an XML representation. So you create an XML generator and you have XML representation of your voice menu. Or you can generate HTML documentation out of this. So now I generated HTML files, and if I open them in browser, well, you see that the voice menu is now is documented here. So I see the menus, submenus, the text and the buttons. And it was generated from the same sources from which I generate the asterisk file that I uploaded to the server. So this documentation never gets out of date because it's generated at the same time you generate the runnable artifact. Well, and the last but my favorite, I can generate Java code. And that Java code can serve as a simulator of the voice menu system. So let's see if audio works here. I'm not sure how. Well,
For products, press 1. For technical support, press 2. For contact information, press 3. For hanging up, choose from this menu. For MPS, press 1. For develop, do you know that JetBrains provides commercial support to MPS users? Choose from this menu.
so you've got an idea, right? So you can actually generate Java code that will simulate voice menu on your computer. So you can verify that the voice menu system meets your needs before you push it to the server. So you can have multiple multiple generators associated with your language, and you can generate different targets depending on your concrete needs. And that's all comes from the possibility to separate the problem domain and the implementation domain. So what we've seen, the voice menu system, was an example of a modeling tool, a tool in which you can model voice menus. There are many tools like that, but the difference between this one and some other single-purpose modeling tools is that this one was created with a language workbench. So this is the main purpose of language workbenches. They are meta-modeling tools in which you model your modeling tools. So you can sort of view language workbenches as language-agnostic, universal, meta-modeling tools. You defined your languages and tooling for a particular domain, and there's nothing inherently domain-specific in most language workbenches, like MPS. They can be used for any domains, and in fact, the customers that you'll hear later today, they come from different industries, different domains. So there are several workbenches out there. Some of them, like MPS, are open source. Some of them are closed source, commercial. I'm going to obviously focus on MPS because that's the one I know best. These workbenches, they have 3 core capabilities. They allow you to create new languages or take existing languages and improve them or change them to your needs. And then you can combine various languages and their improvements together very easily. Let me illustrate that on one simple example. If I say you can implement a new language, then probably the ultimate goal is to implement a language like Java, a general-purpose programming language. So we did that, partly because we needed that in order to develop MPS itself. So here what you see is a piece of Java code. So I write Java, right? This is like Java IDE, code completion, whatever. But this is not IntelliJ IDEA, right? This is MPS with its own Java implementation. So we could implement language like Java, complex, just like Java, in MPS. So this is like the ultimate language. Obviously, most of domain-specific languages implemented with MPS are much simpler than a full-blown general-purpose programming language. But you've got really like a full-featured Java IDE out of this. Then our partners from Itemis, they implemented C. So this is again MPS, but now as an editor for programming in C. So what you see is a piece of C code, and with functions, variables, and so on. Now, in order to illustrate it and the possibility to extend the language, I can show some of the features they implemented in the C code. For example, you can attach physical units to your types. So for this position structure, you can say that X and Y mean meters, not kilograms, not just integer, but real meters. So the type system can then give you errors whenever you're comparing meters and known meters, kilograms. So as soon as you, I don't know if you can see the red underlines. Can you? Yeah, good. So yeah, as soon as you say, well, this is meters, then the type system is happy. So the type system can be extended to do new things, to check for additional things. Or you can add math notations. It's a pity that in most programming languages, you have to abandon this proven notation that mathematicians invented, and you cannot use these symbols to express math formulas, because they make it much more readable to understand, what that thing means. Or you can have a language that represents state machines, as tables. You know, state machines, a thing that has several states, and events can come, and you know, it's supposed to react somehow to, in different states, to different events in certain ways. And this is also an example of combining languages, because now, not only that, in this C code, now I'm using some extra concept for tabular expression of state machines, but also I'm using the physical units there. So it's two languages combined together, and I could, in fact, use the math formula here instead. So I could say, well, actually, this is B. This should be a summary going from, you know, n going from 1 to whatever 100, and now some expression there. So you know, in language workbench, it's very easy to pick languages, possibly from different authors, different vendors, and use them together in one piece of code. Now, in order to define a language in MPS, you have to do certain things. How many of you have some knowledge about how compilers work? All right, quite some people. Good. So you know that a language in memory of a computer needs to be represented as some abstract syntax tree, probably. Right? So even though you see on the screen, you see some textual representation, in reality, well, in the memory of a computer, there's a tree structure that represents the same code. And so when you define a language, you actually have to provide the elements out of which the AST is built. So you need to define a structure of your language, abstract structure, abstract syntax. Also, you have to define notation or notations if the language allows multiple notations. So how the piece of code will look like on a screen. Then type system needs to be declared. Maybe you need to employ some constraints, like a name of a class must not contain spaces. And then transformations, the generator I've shown you in the voice menu example. So some way to take an AST and generate some other AST out of it, or maybe some text out of it. So there's several things you have to do in order to define language. Now, I would like to focus on one thing, on the editor, because this is a part in which MPS is very special. You know, the editor is used to define notations. So how the code will look like on a screen. And you've already seen examples of several different notations. We all are probably familiar with textual notations, right? Block-oriented textual programming languages which organize code in indented blocks of code. Then you can have languages that enrich this with some special symbols which cannot be expressed with ASCII symbols. Maybe you want to have some images as part of your notation. Or what if you want to organize code in tables? Spreadsheets are a very good example of usefulness of such notations. So tables should be a natural part of programming languages. And how about graphical expressions, right? That's, you know, some models are best expressed graphically. Maybe not the whole program, maybe some parts of it. So even that is a notation. And all of that, you know, all of these can actually be presented to the user. The user can interact with them, either with keyboard or with mouse. And they can all be represented as abstract syntax tree inside the memory of an IDE or a compiler. So MPS makes this all possible. All these notations are possible thanks to the technology chosen for the editor. You know, in traditional tools like IntelliJ IDEA, you interact with an IDE through textual document. You write text, and that text is being constantly reparsed by the IDE in order to build the abstract syntax tree. And that structure is then used for code analysis, refactorings, and all the useful stuff an IDE can do for you. And the same thing that is done in the compiler. The compiler takes your sources, parses them, builds an AST, and then transforms it into binaries. Now, we focused on this part, on the interaction with the editor. Because if you have to type your code in textual documents using ASCII symbols, then you're restricted. So how about just getting rid of that and instead allowing interaction between the user and the AST directly? So there is no textual representation, not even on disk. So when you save your code, when you save your model, it saves the tree, either as XML or some binary format. This is what you get on disk. And then it's just loaded in memory and you interact with it. So if you touch the keyboard and type some keys, it's not inserted as a character that the IDE will then try to understand with parsing. Instead, every single keystroke is taken as a command to the IDE, do something with the AST at the position where the cursor currently is. So the rest of it remains same, right? And then during generation, it will generate some source code that compilers can parse. So, but that is not restricting the expressiveness of the languages, so that doesn't need to be changed. It actually needs to hook into existing technology. So let me illustrate that. So I go back to Java, but in MPS, and this is not a textual editor. This is a projectional editor. So it just tries to look like a textual editor, so you can type text. But in fact, every single keystroke is a command to the IDE to change the AST representation. And actually, I can visualize the representation, let's say, of this if statement. If I'm interested, you know what? Show me how it looked like to the computer. What is the AST behind this? So I can just ask the editor, suppress the way you normally visualize that piece of code and show me the AST that is behind it. So now I see that this is an if statement. If I just pick the important bits, there's the condition, which is a static method call. We're calling a method, a static method call to some method called condition on a class called sample. And then if the condition is true, then we've got a statement list, which is executed when the condition is true, and then it's a dot expression, which is a static field reference. The field is called out on a class system, and we call a method printline. So this is like the AST representation of that same piece of code. And I can then go back to the notation. And if I type characters, they are taken as events. So if I type now with my cursor positioned there right next to the curly brace, so typing any characters has no effect until I type something that actually can be there. The only thing that can be there is else, right? Else or else if. So the IDE doesn't actually let me insert invalid code. I can only insert else and then continue with else branch. And if I hit backspace here, it doesn't delete the the ending curly brace. It will delete the whole else branch. Yeah, so I'm editing the code structurally. I'm not editing character by character. I'm actually manipulating the code by the the individual concepts. So then, when you type code like this, integer a equals 1, the right side of that variable declaration is an integer constant with a value 1. So this is the illusion you have on a screen, or the projection of the code, and this is the real code. This is what is saved on disk. This is what is saved in Git. And as soon as you start typing right to, your cursor is here, and you do multiply 2, it will take it as a command that the AST should be reshuffled. And instead of integer constant 1, the direct child of this variable declaration, the initializer, should be actually multiplication of two integer constants, 1 and 2. And if you keep typing +3, then it will create plus as a new root of that little subtree and rewire all the things. Even though when you type it on a keyboard, then you don't feel any difference. So if I do variable a and now do 1 times 2 plus 3, well, it just flows, just goes, even though it's actually several events triggered in the IDE to reshuffle an abstract syntax tree. Okay, so by using projectional editor is not actually our idea. That was invented in the 1970s, I think. But MPS is probably the first tool that allows you to simulate the real text-like experience in a projectional editor. which is in particular very useful in domains where you need either of these. You might need very rich notations, so tables or diagrams or symbols of any sort, or you note multiple ways to look at code, and you need ways to combine code. So for example, and that's the last example I want to show, okay, this one. So you can have a state machine declaration that you look at in a textual way, and you create states and events and transitions and whatnot. And that at some point you might decide that you want to look at the same code differently as a table. So you switch it to a tabular notation and continue editing this way. Or you do editing in one notation and code review in another. Or resolving merge conflicts you do in one notation and debugging in another. So you can have several notations for the same language, for the same piece of code. The abstract syntax tree that is behind this, that doesn't change. It does not really depend on which notation I use to project this on a screen. So I have multiple ways to look at the same piece of code. And you can actually have 3 or more notations, one of them textual, one of them tabular, one of them graphical. They all are basically display the same model, the same piece of code, just in different ways. All right, well, so that was a quick introduction into MPS, so that now you know that what the tool is used for, what it can be used for building, and you know that there is a technology of projectional editor in that tool that allows these fancy tricks with the notation and having more of them and switching between them. So I think you should be able to appreciate and enjoy the presentations of the speakers that will follow. Thank you for your attention.